The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we'll start with the thermal IR camera, and as you can see, it has very strange properties. Who are we looking at here? That's you. And then as it turns on, it's lighter. It goes in automatic gain mode, I guess, and the rest of the image gets very dark. And who's in the picture? Can you wave? Oh, that's Seth. Excellent. I could recognize you in thermal IR. And if you just put a cold finger on your cheek, you can probably see it. And take it off. Yeah, you can see the mark. Things that are completely transparent in visible are actually completely opaque. And this focus is. It's completely opaque. Actually, if you just put your glasses down, you'll see that as well. You won't see it, but others will see.
Yeah, I won't see anything.
So they're completely opaque in.
These are actually glass lenses, not plastic ones. There might be some difference.
Okay.
I don't know.
So it's really looking at about 8,000 nanometer to 12,000 nanometer, which fortunately is also the wavelength in which the human body's the black body radiation of a human body is peaks. So you can do some amazing things with this. Chrysler and BMW are thinking about, or maybe already put them in automobiles, so that you can see things very far away. So one benefit of this, as you can see, is even if you turn off the room light, the intensity will not change. So somebody wants to take the. It's completely independent of the room lighting, right? So because it's not looking at the visible spectrum that's being emitted by these tube lights, but it's a function of just thermal radiation. So at night when you're driving, if there are any animals or even intruders in your backyard, you can detect them with thermal IR.
There's a lot of reflection from the table.
Yes, because remember, this is a very large wavelength. So at that wavelength, the table's roughness disappears and it becomes highly reflective. Is this... Last time I tried to focus, something went wrong. Yeah. All the people with glasses look very cool.
What is the lens made out of?
So that's a good question, because a typical glass will not transmit thermal IR.
We showed, yeah.
Yeah, that's a good demonstration. So a lot of these lenses are made up of germanium, and also certain types of plastic can be used for this, but the image quality is not that great. But germanium is very common.
Does this have different focal characteristics because it's such long wavelengths?
It has, you mean 8 to 12, just in terms of the ratio. So it's like 300 to 400 is the same as 8 microns to 12 microns. So it should be able to focus in the majority of that band. But because you need a larger lens, the depth of field is pretty narrow here. So, with this you can build a glass detector. If I look outside the window, for example, it's completely opaque. Can you wave, last person? Yeah. So it's completely opaque, the glass. So you can build a glass detector. You can take a photo with a visible regular camera. You can take a photo of this, and if it's opaque in one but transparent in the other, then that's glass. So you can do all kinds of interesting things. And again, if Matthias is successful and other companies are successful, not in 5 years, but in 6 years, it might be in your cell phones. Thanks a lot, Hero. All right, so let's continue here. Has anybody seen this snake illusion before? Yeah. Does everybody see rotating snakes?
No.
No?
I think it'd be like head on. Yeah, it doesn't work.
At an angle?
No? Yeah.
All right, maybe I can. How many of you can see it? How many of you can see, and how many cannot see a rotating pattern? So, okay. I've heard this before, because this is different than those really annoying, random dot stereograms, the magic eye, that a lot of people have trouble seeing. But this is not based on the same principle. It's based on a different principle. It's just looking at the decay in your retina, how long it takes for your retina when it's doing saccades to basically do center surround subtractions. So it's a very different principle. So those of you who cannot perceive motion in this one, do you also have problems with magic eye?
Yeah, I can't see the track.
Yeah, I think magic eye is probably a lot. How many people have problems with magic eye? Yeah, I think that's a lot. But so it looks like the two sets don't have any relationship. Two subsets. So how can I take a photo of a scene that has motion, print it on a piece of paper, and create an illusion of motion? That's a research problem for your project.
You could print that out.
Yeah, but that's only for this particular scene. I want to take a photo of a car moving or somebody running, and I just want to take a couple of, maybe 5 frames of that video, and create one photo out of that, so that it looks like the person is constantly moving. I think we can put on the lights again. Let me skip this. So, all right, here was that question, and how can I look around a corner? So this is actually a huge project in our group of how can you look around a corner. And the way we do it is we actually use some really cheap devices, about a so-called transient imaging camera, where we use a impulse response of a scene. We transmit a signal. Maybe I'll use a laser pointer. We transmit a very tiny pulse, which reflects off of the door, bounces around inside the scene, reflects back from the door, and it is captured back again at the camera. And by analyzing this multi-bounce reflections, we can figure out what's inside the room by just looking at the door. So the devices are extremely cheap. We need a femtosecond laser that costs about $200,000. And we need a photo detector that costs about $3,000, but we found some cheaper versions. And then we also need a 10 gigahertz scope that's about $50,000. So, after about $250,000, you can look what's around the corner. So, maybe not in 5 years, but maybe in 10 years or 20 years, you will have devices which will allow you to look around the corner. And right now in our lab, you can do it. And this is going to completely change the way we think about photography, because line of sight is, almost a fundamental assumption. We think it's almost, a lot of us think that's one of the laws of physics. We can only see things that are within the line of sight. But we are not violating any laws of physics. If you're violating the laws, you're welcome to report us. But this is possible. So throughout this class, what you'll see is that the laws that you take for granted and the laws that are shackling the way you think about visual capture and visual displays are just there because somebody taught you that. But you can challenge all those assumptions with modern tools, whether they're sensors and optics and modern computational methods.
What's the point of the femtosecond laser if it has such a short coherence length? You can't really be using the laser.
So the reason why you need an extremely short duration laser is that if you just imagine you build a camera. So those cameras, this time of flight camera that Jay was showing, emits a pulse at about 50 megahertz. So it's 20 nanosecond repetition, and light travels how much in 1 nanosecond?
1 millimeter per microsecond.
Yeah, but that's too complicated. How much in 1 nanosecond?
About a micron?
No, much more. More than that?
Just 100 meters.
A foot.
It is a foot,
Right?
that's right. That's
Okay.
right.
So,
Sorry.
a very
Yeah.
simple thing to remember.
Right.
Light travels 1 foot
Yeah,
in
yeah,
1
sure.
nanosecond. And what about sound at room temperature? How much does it take for sound to travel 1 foot? You know all the numbers. It's 330 meters per second for
10 milliseconds.
for sound and 3 times 10 to the 8 meters per second for light, but that's too complicated to think about. We want some simple rules of thumb. So
10 milliseconds.
10 milliseconds for 1 foot. It's 1 millisecond, right? So very easy to remember. Light travels 1 foot in 1 nanosecond. Sound travels 1 foot in 1 millisecond. So light travels 1 nanosecond. Sound travels 1 millisecond. Unfortunately, there's nothing that travels in 1 microsecond. If somebody comes with a new physical propagation channel that travels 1 foot in 1 microsecond rather than milli and nano, then you'll see a completely new range of applications. So you have electromagnetics, EM spectrum, that's 1 nanosecond for 1 foot, and sound 1 millisecond for 1 foot. So sound is too slow and light is too fast in almost everything we want to do. And so here, we want something that's even faster than traditional light propagation. So in this room, if I just send a beam of light, very narrow pulse, by the time it goes to that wall and comes all the way back to me, let's say this is about 20 foot, it's going to take me about 40 nanosecond to come back. On the other hand, if I just want to see, where somebody's within a couple of feet of that wall, then I need to start measuring in picoseconds, not 10 to the minus 9 seconds, but 10 to the minus 12 seconds. And that's why you need something that's extremely fast to be able to do any. So a traditional time-of-flight camera will just look at this door, and that's it. There's nothing more you can do. But if you want to look at interreflections, then you need to be able to resolve time at a much higher temporal resolution. So femtosecond lasers are not something, they're not exotic. They're used in OCT, they're used in 2-photon microscopy, and they're used in a lot of other applications, but still not consumer applications. They're used in medical imaging. And once they become solid state and easy to carry, we can do that. A lot of LiDAR also happens in not femtosecond, but nanosecond ranges with very high power. So if you can look around the corner like this, what about looking around a beautiful artifact like this one? If I have a bottle, where's my bottle? If I as a human, when I look at this bottle, I look around it and I create a mental representation of what this looks like. But if I capture a photo, it's going to be only from a single view. It's going to mimic my perspective and so on. But my mental representation is actually something like that. Right? So how can we build a camera that takes an object and creates a rollout imagery like that? Now, this particular object is straightforward. I can just put it on a flatbed scanner and I can just roll it. But some other objects are not so easy. This object, for example, which is not completely cylindrical, has doesn't have a constant radius around its axis of rotation. So if I just roll it on a flatbed scanner, I will not get that. So maybe I need a special camera, or I can use my existing camera and use some interesting tricks, computational tricks, to create rollout imagery. Another research problem. And I'm sure a camera company would love to have this feature. As you have all the boring features, AV, TV, panorama, movie, and then you have rollout mode. So that will be fun. And maybe you can do it with an ordinary camera, or maybe you can do it with a femtosecond laser if you have $250,000. All right, so let's do a very fast-forward preview of the rest of the class. And here I'm mostly going to talk about what's the input, what's the output, I may not go into the detail of exactly how this works because, again, these are teasers of what's coming in the class. And what I would like you to think about during this preview is how this applies to some problem you may be already working on, or what are some parallels with things you already know. And again, most of these techniques will be about changing the rules of the game. If you have a project where you're tracking your fingers with a cheap webcam and it's not working because when the light changes or a person with a different skin color walks into the scene, there are solutions here. If you're worried about how to track crowds, there are solutions here. You want to see what's behind a glass that's murky and diffuse, there are solutions here, and so on. And of course, there are really interesting devices that you could use in new forms of photography. So here's a really simple example of how we can get started. So Paul Haverly in 92, simple idea, take an object, turn on the flashlight on the left, turn on a flashlight on the right, and then you can form this image by combining these two. How would you do it? This looks like a blue light and this looks like a red light. Just from these two input photos, you want to create this one. Yeah?
Just mix the channels.
Exactly. Just take the blue channel from here and red channel from here. That's it. And creates this beautiful relighting artifact. So that's going to be actually your assignment number 1. Yeah. Just a warm-up assignment. All you have to do is take an object and take 2 or 3 photos by moving your light source, and then mix and match the color channels to create very beautiful color artifacts. And this will help you to get your whole pipeline for rest of the semester going. You will have your own camera. You're welcome to use your regular camera, like even a cell phone camera. But ideally, you should start using a camera that has more manual controls. And it will get you set up with your MATLAB or Java or Flash, whatever you want to use, C++, OpenCV. There's a lot of easy ways to do this, but I would like you to set up your environment so that this type of operations are very easy to do. And that will be your assignment number 1. Relatively straightforward. Of course, this is what you would do at home, but if you have a couple of $1 million, then this is how you would do it in the Hollywood. So this is a project from Paul Dabavek and his group, really excellent set of work where they're building different light stages. And instead of turning on one light at a time or moving it manually, they have a dome with about 150 lights. And then they use a high-speed camera here and turn on one light at a time, so they can photograph this actress under 150 lighting conditions in 150 frames very quickly. And then again start from the beginning and so on. That's one way to do it. The other way to do that is, let's say all you want to do is insert this actress in a scene that may have been shot somewhere else. So she's in LA and you want to insert her on top of a photo that was actually taken in Milan. Now, if you just take the photo and superimpose it, it looks very fake because the lighting doesn't match up. So the trick they use is, some guy puts a shiny sphere in Milan and takes an environment map of that courtyard. Then you feed this image onto these lights. So if the left corner is reddish, the light on the left side of this dome is reddish. If it's yellowish here, and so on. So for all this 4 pi, you turn on the lights correspondingly, and now she's bathed in light as if she was in that courtyard in Milan. And now if you take her photo and cut out and superimpose on that background, it will look more realistic. And they have done videos where they took this shiny spheres, and Christmas is coming up, so you can pick up your shiny spheres, and you just put the shiny sphere and move in the courtyard with it. So you're constantly capturing the environment map as you move along. And in the scene, she just stands in one place, but the dome is lit up by the environment map that was captured from these shiny spheres. So in a video sequence, it appears as if she's walking through this environment. At least she's lit up as if she's walking through this environment. So these are some of the tricks that are being used currently in major productions. So Matrix, all the movies that came in the last 10 years or so are using this particular mechanism to create mattes that have correct lighting, match lighting, sorry. And if you don't want to spend $2 million, back to something really cheap, you can, to create the silhouettes and so on, you can use a multi-flash camera. So here are some cameras that you can buy. This is, I believe, a Lumo. Yeah, this is a Lomo. So I think it's about $30. And what it does is, let's see if it's. Did the lights go off? So when you release the shutter, it we're too cheap to put the film inside, so we have to manually move it around. I think we're out of battery here, unfortunately. But anyway, when you release the shutter, it takes 4 photos by exposing one pinhole at a time. And at the same time, because it cannot recharge the flash that quickly, the simple solution was to actually put 4 different flashes. So this shutter goes off, then this light goes off. Then this shutter goes off, this light goes off, and so on. So it takes 4 pictures. Now, instead of putting the lights all in one place, if you place them around the camera, you can do something interesting. When the flash is to the left, you know that we get a very annoying slivers of shadow in an ordinary photo. Now, if you intentionally place the flash, so you can see it here. So there are all these slivers of shadow at depth discontinuities. And you probably see it in your own photographs. If you place the flash intentionally to the right, then the slivers move to the left. If you put the flash at the top, the slivers are shadow slivers are at the bottom, and so on. So by taking these 4 pictures and analyzing those tiny slivers of shadows, you can figure out where the depth discontinuities are, where the foreground is separated from the background. Not just the whole person and the wall behind them, but also any internal changes. So if my hand here, it will create a boundary between my hand and my body, no matter how close or how far I am from that. So by doing that, you can estimate all the shape contours, and this is the edge map you would get if you had an ordinary camera, and this is the edge map you get with a multi-flash camera. So now, if you have an application where you want to track a hand or track a gesture, instead of taking a standard 2D image, if you take a multi-flash image, you'll get very clean contours, and from those contours you can build an HCI application that will perform very well even in strange ambient light. And I guess it's independent of the color of the foreground object. It only relies on the shadow. So again, if you want to track a hand, you're not dependent on the skin color anymore. So you can play these tricks to overcome the limitations of a traditional 2D camera. Let me skip ahead a little bit here. Another assignment we'll be looking at is this virtual optical bench. And this is a very nice toy that Andrew Adams at Stanford put together, which is a flash-based application where you can insert lenses and occluders and mirrors and ray emitters and so on. And you can basically do a very quick setup, very quick optical design of a setup. And what we'll do is we'll start with this. One option is to start with this his source code, and modify and insert a few more optical elements, maybe a prism, maybe a grating, and so on. Okay. This will be one option, and as I said, you'll have multiple options for each assignment. So, thinking a little bit more about lenses, one concept will come across quite a bit in this class is light field. And now this particular camera that we saw, 5x5, that Rollup was showing us, is actually a light field camera, but that's made up of an array of cameras, physical cameras. And what we're going to do instead is we're going to take an ordinary camera and convert that into an array of virtual cameras. So this is an array of physical cameras, but it's expensive. Instead of that, we'll take an ordinary camera and convert that into an array of virtual cameras. So this is how it works. You have, in a traditional camera, if the object is in sharp focus, the radiance along each of this direction is convergent on a single pixel. So you get a very sharp image of that point. But any information about the radiance along each of these directions is completely lost. Okay? So you get a 2D image. You have a 3D scene, you get a 2D image. So it's flattened. The world is flattened. A trick you can do, which was actually invented by Ted Ellison and his student Wong, that just left, is trying to capture the radiance along each of these directions. So how do you do that? You just displace the sensor a little bit back, and in front of that you put a microlens array. This is the same microlens array you use in lenticular displays, those displays that change with viewpoint and so on. So if you put that microlens array, then as you can see, each of this ray is actually incident on a different pixel. And then you can capture the variation along each of the incoming rays. Now, why would you care about capturing each of these rays? It turns out that the appearance of the world coming through a lens can be completely described, geometrically completely described by a four-dimensional function, which is this light field. And that's a very powerful concept, because if you do capture this full representation, then you can do, that's all you could ever capture. Once you have this 4D representation, you can manipulate that in many interesting ways. So Ted Ellison and Renning at Stanford, who also has a company now called Refocus Imaging, are building this type of cameras with lenslet arrays. Now, how did the Stanford team do it? They started with a medium format camera with a digital back, and on the digital back they put this microlens array where the pitch of the microlens is 125 microns. So pixels are about 9 microns. So under each square tile they have about 14 by 14 pixels. So again, going back here, under each microlens they have a 14 by 14 array of pixels. So what they're going to do now is they're going to take the 16 megapixel detector, 4000 by 4000 pixels, and have 292 by 292 pixel array, microlens array. Under each microlens, 14 by 14 pixels. Okay. So at the end, they have this one 16 megapixel image, which after reshaping gives you this 292 by 292 pixel image, one under each microlens. Okay, so we have given up a lot of resolution. From 16 megapixel, we're down to 292 by 292. Okay, but with that, we can do some amazing things. We can do digital refocusing completely in software. Okay, so you have given up a lot of resolution, but now you have complete control over where you can focus. And as you can imagine, this is the same question you asked earlier. From this, I can also estimate depth, because depending on when things come in focus, I can assign a depth to each pixel. So suddenly, from a ordinary 2D sensor, I have a camera which has how many virtual cameras? Here we have 5 by 5. How many virtual cameras here? 14 by 14 cameras. What is that? 228? No, 196.
But then each camera is 292 by 292.
Exactly. It's very low resolution. And so first kind of complaint is, yes, it gives you all this power, but very low resolution. And the argument nowadays against that is whether you have 6 megapixel camera or a 16 megapixel camera, it doesn't really matter. We have reached, we have diminishing returns after 6 megapixel. So why not use those pixels for capturing some other information? So that's what makes it extremely powerful. And refocusing is only one. Depth sensing is another. Interaction, dealing with aberrations in the scene, a lot of interesting things you can do. And again, this is starting with a static 16 megapixel camera, so it's not video rate. But this one is video rate, although it's only 25 virtual cameras.
Is the Microlens something that could be flipped in and out of the way so that you can combine images?
You could do that. Unfortunately, the precision that you require is micrometer precision. So it's a little bit challenging. But you're right. I mean, I'm sure when cameras were designed in the beginning, they had physical apertures that couldn't be changed. And over time, people figured out how to create variable apertures and so on. So creating these dynamic elements is going to be the key for future cameras. And people often ask me, what are the things that you're going to see in the camera next? And we already have high dynamic range. Next is color, and we get a lot of journalists asking questions like this. The future of photography. A lot of popular magazine with a lot of junk in it, including people who are not credible with pictures in there. So, to me, the answer to that question is light fields. That's going to be the next big thing. If you think about the top 5 features that will appear in a camera, it's exposure, color. Number 3 is light field. So we'll see how long it's going to take before we have a full-fledged light field camera as a consumer device. And again, initially they're going to say, hey, but it's only 292 by 292 pixels. But my guess is that by then we won't care about the pixels, number of pixels. So my group was extremely inspired by this work in 2004, 2005. But we thought this is very challenging to create because you need a microlens array. So we said, instead of using a microlens array, can I just print a transparency at home and create this light field camera? So that's what we did, which is called a mask-based light field camera. And this is how you do it. You start with a medium format camera, in this case a Mamiya. On the digital back, you just remove the IR filter. And it turns out there's already some glass on top of the sensor, which is about 1.2 millimeters thick. So you just drop a transparency on top of it, snap back the IR filter, and that's it. For about $2, you can convert a medium format camera into a light field camera. And the design looks something like this. Traditional camera, traditional sensor, but about 1 millimeter in front of it, you have a printed mask. Very cheap. Using that, we're able to convert this 2D camera into something that captures a 4D function. And the concept is actually very similar to radio frequency heterodynamic. The reason why you can listen to multiple radio stations on a single antenna is because all those stations are transmitting using either amplitude or frequency modulation. And then in software in your car, you can tune into any one of those channels and decompose and decode any one of those radio stations. And what we're doing here is very similar. We are doing that in the optical domain, and that's why we call it optical heterodyny, in space, not in time, where you have the object, it's forming an image on the sensor, but we're going to take this photographic signal, which is 4-dimensional, not 2-dimensional, and use this carrier and then create a modulated signal. So again, for those of you with a communication background, this analogy will work. And then in software, knowing this carrier, we can demodulate that and recover this 4-dimensional light field. So it's possible to do it with a very low cost. Sorry, can you hit the lights in? Yeah, maybe the other one. Thanks. And this is a photo that we capture with our mask-based light field camera. If you zoom in, it has the in-focus parts are actually okay. The out-of-focus part has this really strange encoding because of the high-frequency mask. But then in software, and this is how the mask looks like, the printed mask. And in software, it turns out that by applying appropriate signal processing framework, we can decode that and recover it. So this is a 2D frequency transform of a traditional photo, where most of the energy is in the baseband. And after applying this very high frequency mask in the optical path, it actually encodes this information in this particular case, a 9x9 windows of the Fourier transform. And this intentional aliasing or heterodyning allows you to capture the additional 2 degrees of freedom. And so the process is very simple. You take this photo, which is about 4 megapixel. You take its 2D Fourier transform. You reshape that to a 4D function, and then you take the inverse Fourier transform to create this 81 virtual cameras. In this case, 9x9. This was 5x5. This is 9x9. And the best way to show that is to see how that photo will look like when there is a small parallax between each of the virtual cameras. And again, from these 81 images, you can estimate depth, you can create refocused images, and all that. The same thing that Roth was showing for refocusing from here to infinity. Infinity, back and forth. So you can do that with an ordinary camera with this a small change with mask. And all the software is online. And this will not be part of any assignment, but you're welcome to take that up as an assignment or as a project. Maybe we can get the lights back again, sorry. What are some other things you can do? As I said, in terms of the desired camera features, it's dynamic range, color, and then light field. In terms of color, Ankit Mohan, who's a scientist in our group, that was this part of his thesis, he said, let's think about color as not multispectral imagery, but more like an audio synthesizer. You know, if you have an audio system, and whether you're listening to rock or jazz or pop or country music, you tune your bass and treble accordingly, or maybe you have a profile, so that the frequency profile of your synthesizer is appropriate for that particular type of music. The same thing should be possible for photography as well. If you're you're in the woods, you would like to look at most of the green channel to see how the variation of different leaves and all the nature is captured with sufficient variation. Maybe you don't care so much about reds and blues there. On the other hand, if you're near an ocean, maybe you mostly care about the blue shades and so on. So what I would like to do, and photographers do this all the time. They carry a set of filters with them, and if they are looking at broad sunlight, they put one type of filter. If they are on a beach, they put another filter, and so on. What I would like to do is create a knob right on the camera, just like an audio synthesizer, that says boost red, suppress green, and create any profile you want. So creating this programmable wavelength would be extremely powerful. So Ankit's project basically achieved that, which he calls agile spectrum imaging or programmable wavelength imaging. So it's a very powerful concept, and hopefully it will appear in cameras as well. You can imagine this is very useful for medical imaging. When you go to the dentist and they're putting what's it called, enamel, to change the color of your tooth.
The whitening?
Yeah, the whitening. What is it called? Enamel? Bleach, yeah. And the problem with that is in the dentist's office, everything looks fine, but you go elsewhere and somebody takes a flash photo, and the guy with the teeth, fake teeth or bleached teeth, looks extremely different, and that's metamer, because the wavelength profile of a flash is very different from the wavelength profile of tube lights. So what doctors would like to do is see the neighboring teeth under all different lighting conditions, so that they're still matched, for example. And this is true of, I did show you the vein viewer, where you want to see the veins, and depending on oxygenated or deoxygenated blood, the hemoglobin, you can figure out which veins should be used to poke the needles. And again, that can be looked into very narrow wavelengths. So they don't know, in that case, they might know, but in different applications, they may not know a priori which wavelength you should be looking at. And so by creating this programmable spectrum camera, you can do, again, very interesting things. So we'll be looking at that. Glare is another challenging problem, right? If you have a bright sunlight, it's creating glare. Sometimes it's for artistic effects, sometimes it's just annoying. So can you take a photo that has this concentric rings because of glare, and either boost the glare, create some cheesy effects like it's a rainbow transition here from blue to red, or actually suppress that glare? Again, all from a single photo. So it turns out glare can also be captured using a light-filled camera. If you have a bright light, such as this, let's see, this is a bright light and this is some other scene. The bright light will create a sharp photo, but because of interreflection, the Fresnel reflection in the lenses also create a glare effect and contributes to the wrong part of the image. But again, what we will learn in this class is that by doing this 4D sampling, you have complete control over the lens flare and certain types of glare. This again, light field concept for camera array. Stanford and Professor Mark Lavoie are the world leaders in thinking about light fields and light field cameras. So they built this amazing camera array, the electronics for it, the optics, and so on. In this case, I believe about 51 cameras. And then they can do very interesting things. So here's a scene. You have about 51 cameras looking at a scene behind the bushes and trees, and this is how it looks. Focus on that part, and by doing refocusing, you can see what's behind those trees. So this is you're just doing virtual refocusing in the scene, and by doing that, by using an extremely large aperture, you can see what's behind this bushes. And this is pure refocusing. You can do additional computational techniques to recover what's behind the trees. So a lot of things in computational camera and photography are really about magic. How can you look around a corner? How can you look behind the trees? How can you look inside the body? And so on. So that's why I like this field. It's like magic tricks. And somebody shows, once in a while, you come up with your own magic trick. And some other times, people show you a magic trick, and different people figure out, different ways of achieving the same magic. And that's why it's such a vibrant new field. The way synthetic aperture works is, the same way if I hold a needle next to my eye, not poking my eye, but just right next to my eye, then if I focus on the needle, I'll see it. But if I focus far away, then this needle just becomes blurred, and this does not occlude what's behind. And the same concept is for synthetic aperture. It's used in radar, it's used in astronomy, and all you have is an array of receivers, whether it's antennas or whether it's microphones, whatever it is. In this case, cameras, array of cameras. And if you have a very, very large aperture, then a point that was occluding some point behind ends up being extremely blurred. So it does not impact what's behind that. If you have a very narrow aperture camera, you cannot do that, but you can do that if you have a very wide aperture camera. So we saw that. Okay. So what about medical imaging, such as computer tomography? And we're jumping from photography to tomography. Both are recording. One is recording light, the other one is recording slices. It turns out you can use very similar principles. So what's happening in tomography? You have an X-ray source that's emitting in an omnidirectional fashion, and you have detectors here that are. Should I use this screen? Because most people are. Which screen is better for majority of people? That one?
Yeah,
sorry.
give it.
All right, I'll use this one. Sorry, Rod. This one was convenient for me. you have an X-ray source and you have an array of detectors. And basically, when you put your head inside this X-ray source, the tomography CAT scan machine, the X-ray source spins and the detector moves in the same direction, right? And let me show you a video of how this actually works. Let me start from the beginning. All right, it's been opened up, so you know what's going on. That's what's happening. Imagine your head is inside that. All right, that's what CAT scan machine is doing. And while they put an eye patch and you're just resting inside. It's basically a jet engine. It's totally crazy. Okay, it's totally unnecessary. We're in the 21st century. We're in the 21st century, and we're building this, devices that are based on 40-year-old principles. It's unbelievable. It's totally ridiculous. What we need to do is completely rethink how this imaging is done, and use new computational methods to overcome this totally bizarre, multi-million-dollar devices. So that will be one of the things we'll be learning in this class, how we can take principles from signal processing, photography, scientific imaging, and kind of mix and match them to build new things. Borehole tomography, another very interesting problem. All you do is you create, you drill a hole, you put explosives here, and you put sensors here, or in this case it's audio. And then you fire off these bombs effectively. And based on how long it takes for sound to travel to these detectors, tells you what the density of material, whether it's rock or oil or other types of formations. And from that, the oil companies can figure out if what type of oil there is and where it is. So you can create a 3D map of what's inside. Again, multi-billion-dollar situations. Microscopy, deconvolution, also used in photography, also used in machine vision, computer vision. We'll talk about that. Coded aperture imaging, an idea that was used in astronomy because astronomy, you're looking at gamma rays and X-rays, and you cannot build lenses for them to form an image. So you can either create an image with a pinhole of the sky, or you can use a coded aperture so you can collect more light. Now that idea, we'll learn about that, can also be used for photography. So what our group did was we used a coded aperture in the lens. Instead of having a clear disc-like aperture, we put you can't barely see it. I'm sorry, it's supposed to go this way. You have a coded aperture which looks like a crossword puzzle-shaped mask. And from that you can take a photo, again, which could be out of focus, and then digitally refocus that. So this is, out of focus photo, this is in focus photo, and you can capture, the glint in the eye or even a strand of the hair. Again, very minor change to the camera. And if you, originally we were talking about, successful biological vision, if you think about the simplest possible biological vision, which is a single pixel detector in a worm, right? Just a single pixel. It's in muddy, mashy waters, looking for food or maintaining its orientation. It doesn't need a full-fledged camera. It just has a single pixel detector. It just knows if there's light, there's no light. If there's light, how much light there is. So you know when it's day, when it's night, which way is more light, which way is less light. But even that single pixel detector has some very interesting optics in front. It has this very intriguing shielding pigment in front of it. Can anybody guess what's the reason for that? How does it benefit to have some random pigment that's blocking the light from different directions? For orientation. So if this worm wants to maintain an if there's a light source, and if the sensor was hemispherical, then if this worm moves a little bit, there will not be much change. But if you have a very high frequency pigment, if this worm moves even a little bit, there'll be a big change in the lighting. Right? It's look as if you have a very high frequency mask and you're looking at the sun. As you move, the light goes up and down. So the worm knows that as long as it's maintaining the same level of light, it's maintaining its orientation. Right? That's all it needs to do.
Does it also increase the effective dynamic range of its sensor
It's
as
possible.
a kind of like neutral density filter along certain directions and less?
It's possible.
Yeah.
It's possible. Maybe when it's looking at one direction, it's too bright, so it tries to block that. We don't know. And if you read this book, there's a beautiful book called Animal Eyes by Land and Nissen, which we'll have a whole class on animal eyes. I think it's the 7th class, if I remember correctly. And we'll discuss all different types of animal eyes and why they do it, whether it's eagles or land creatures, underwater creatures, worms, and all that. And frankly, most of these biological visual systems are based on hypotheses, and they're verified in a very scientific, but at the same time very primitive equipment. And one of the great projects would be to take some of these worms and put it in a controlled lighting setup to really verify if this is how they work. That will be a lot of fun. I'll provide the worms, don't worry. So, this coded aperture is, somewhat similar. Let me skip over this part because we talked a little bit about how to use mask. All right, wavefront coding. This is a concept that was invented by Kathy and Dowski in 1995 for shaping light, or shaping the wavefront of incoming light. So you have a traditional imaging setup, you have an object, you have a sensor, you have some lenses. What they proposed is placing an additional optical layer in between, which is not a lens or a prism, but has variable thickness or variable refractive index. Okay? The simplest way to think about that is the light in the top part might travel at one speed. Remember, if you have a glass with different thickness or different refractive index, the light is going to slow down, right? And when it comes out on the other side in air, it again go back to 1 foot per nanosecond. Very good. But before that, it's going to travel slightly less than 1 foot per nanosecond, right? If it's 1.5, it's going to travel, 1 by 1.5 of foot per nanosecond. So anyway, so by adding glass of different thickness or different refractive index, each of these rays are going to be slightly out of phase with respect to each other. So when they combine on the detector, they will either they will interfere and add constructively or destructively. And from that, you'll form new images. Right? So this is how they explained it. And if you read the papers, unfortunately, they're very difficult to understand. And what you'll realize is that instead of going into the math of Fourier optics and so on, in this class, we will use very simple ray diagrams and understand how this works in a very visual manner. Okay. So basically what wavefront coding camera does is, in a traditional camera, rays converge to a single point and you get a sharply focused image. So if the sensor goes in and out of focus, you get a large blur. In case of wavefront coded camera, actually you never get a sharp spot. What you get is basically, think of taking a lot of straws, instead of all of them converging to a single point, taking them and then twisting them so that they go out again as the straws, but in between there's a part where all of them are, the cross section of them is roughly. Okay? And by doing that, it turns out for sufficiently large depth range, and the defocus is equivalent. And we'll study this in detail and how this works and how you can use the same techniques for new types of photography and scientific imaging. Now, this is also a very hot topic in night vision goggles, by the way, where they want to wear night vision goggles that when you look far away, it's very clear. And again, night vision goggles have very large apertures. And when you look closer, if you want to read a map, for example, it should still be in focus. So how do you create a passive device that can focus at infinity and very close up at the same time? And they have been using wavefront coding as well. Wow, I can barely see this. All right. This is the project called Decoding Depth via Defocus Blur. This is from Colorado, from Rafael Pashtun and Yoav Shetner. And this is very counterintuitive. If you take a point light, and I wish I could do this experiment. I can do it here, but it'll take some time. If you take a point light and form an image on this particular guy, please.
Do you want a little flashlight?
Yeah. Exactly. Thanks. So as you can see here, that's the image plane, right? As I move it in and out, its shape is going to change. The spotlight. Now imagine, and that's what happens in the bottom part of the image. As you are in sharp focus, you get a small spot. As you go out of focus, you get a bigger disk. But the kind of optics this group designed, when you're in focus, you see two spots that are left and right of each other. And when you go out of focus, these two spots rotate one way or the other way. If you're closer than plane of focus, it rotates in one way. If you're away from out of focus, it rotates the other way. So this rotational point spread function is a very powerful concept. And right now they're using in microscopy for resolving fluorescent beads at nanometer precision. But it could also be used in photography. Nobody knows how to do it. This could be one of the research projects. And we can get some of these prototypes from our colleagues. So it's a lot of fun to play with. Another interesting thing we'll be looking at is relationship between Fourier optics and ray optics. Now, in high school we were taught, there is particle and wave duality and a lot of confusion, and we have to write, in high school we have to answer questions of what phenomena can be shown in particle way and what can be shown in using the wave propagation model. And one of the standard answers was, if there's interference or diffraction, then it can only be explained with Fourier optics, not with particle nature of light. That's too simplistic. It turns out that you can really show that they are the duals of each other and explain diffraction and interference and all these mechanisms using purely ray propagation. And so with Sabaik, his name is not here, Sabaik O and George Barbasis, who are mechanical engineering, we have a project where we have created a so-called augmented light field, which can actually support all the wave optics effects as well. So traditional light field that we just described earlier, where you can capture with an array of cameras and so on, can do this position angle representation, the 4-dimensional representation. And at that time I made a claim that if you can capture this 4D incoming function, you have captured everything geometrically that has come through the lens. So it's a complete representation of the light. And some people would say, wow, but then you're not capturing the phase and you're not capturing all these other things. But it turns out that using the same exact setup, you are also able to capture phase. The 4D representation actually encodes the amplitude and phase of the incoming wavefront. And so we, simply by using different mathematical terminology, we have augmented this light field representation to also model wavefront effects. So we'll study that a little bit. What about photographs like this? If you look at this heater, it's creating this beautiful streams of hot air. Also this lamp from the lampshade. Again, we are trying to visualize that cannot be seen with the naked eye. So this is known as schlieren photography, which is again looking at very minor changes in the optical path. In this case, because of heat, if you're on a hot day on a highway, you see the mirage, but that happens extremely high temperatures. Now, even at not so high temperatures, you can actually capture this mirage and create very beautiful photos. So this is schlieren photography, and we'll be studying that. Polarization is beautiful. You may have used polarization for taking photos of the sky or on water, but underwater photography can be dramatically improved with polarization. So we'll study that. We'll also study some new type of sensors, not just two-dimensional sensors, but these other sensors, as I said. Single pixel camera, compressive sensing. How many of you have heard about compressive sensing? Right? There's a lot of hype about it. And again, if you read the papers, sometimes it's very difficult to follow what exactly they're trying to say and how it's done. But as you will see in this class, you'll get the whole idea of compressive sensing in less than 5 minutes. And we'll go through what works, what doesn't work. And actually, Rohit is working on a project which shows that, hopefully will show that compressive sensing is actually not such a great idea for imaging, but it is good for something else. And we'll study what that something else is when he and Ashok's project is reaching some mature stage. So very exciting ideas there. So the original idea was to create a single pixel camera. Instead of creating a megapixel camera, you have a single pixel that's going to take a coded combination of incoming light. So this may be a scene. It's being focused on the whole reflected mirror array, and you're just going to flip this mirror on and off. So the light you collect will be a product of the scene with this vector. And if you change these flips, you get some other sum. You're going to take a linear sum of incoming light. And if you take millions such measurements, you can reconstruct a megapixel photo. But the claim of this group from Rice is that you don't have to actually take a million readings. You might be able to get away with only 10,000 or 100,000 readings. So you can capture a megapixel photo with possibly only 10,000 pixels of a camera. And we'll look into that and what part of that statement is true and what part of the statement requires more analysis. And you'll also see that this can be used in a lot of other situations. So, for example, my group has built a strobing camera that can be used for laryngoscopy, where in a traditional laryngoscope you use very high-speed strobing to slow down to visualize the motion of vocal folds. But we just came up with a new method that is dramatically simple and uses dramatically less light, so you don't burn your throat when the doctor is looking at your vocal folds. And that's based on compressive sensing. So let me stop here because we're almost at 4:30, and we'll come back and look at some of this other projects. So these are the kind of project assignments you will see. Relighting, the first one that I already described. Dual photography, where you can read your opponent's card. Virtual optical bench, light field capture, high-speed imaging, thermal imaging, multispectral imaging, range imaging, and so on. And then a completely open-ended final project, which you can choose in any area. This is the first assignment. The instructions will go out on the Stellar webpage. Please make sure you have the sign-up sheet. Has it gone around? Okay. Please make sure your name and email is on the sign-up sheet. If you don't get an email from me by Monday morning, please send me an email, which means that I could not read your email address correctly. So yeah, this will be some of the assignments you'll be doing. And this one is due on September 25th. And every class, we're going to, starting from next class, we'll have a volunteer who takes notes for the class and posts it. Because a lot of our discussion is going to be on the board and so on. I'll send out specific instructions. So we need a volunteer for next week. You want to do that?
Yeah.
What's your name?
Sam.
Sam. All right. Sam is going to volunteer for next week, and we'll decide who's going to do that.
Nice to meet you.
Yeah.
Are you planning to live in Raskar?
Sorry?
Do you have any plans of having
be kept on the size of the screen?
Probably not, because most of the people are going to be, many people, not most, but many people are going to be listening. So as far as I know, it's not going to cross the limit. But if there is a cap. I don't think it's going to reach the cap. So. There's a cap of 30, so I don't think it's going to reach that. And we'll see some of these demos next time.